Hi, welcome to Electrochem 2. Today we're going to go ahead and today we're going to talk about Electrochem, and we're going to talk about thermodynamically favored reactions, in which you know that if we have a thermodynamically favored redox reaction, what about Gibbs free energy? We're going to talk about a special kind of cell called concentration cells, and we're also going to talk about electrolytic cells. And so, if you look at this, I want to talk about this. You have one of these standard reduction potential tables, and if you look at it, looking all the way down, as the reduction potential tables go down, they approach zero. At zero, this is what all these cells are based on. And if you notice this reaction, you have hydrogen gas, and this is the actual cell for that. And all those other reactions are based on hydrogen being zero. Now, if you look at this, we have hydrogen gas in this glass electrode. There is a platinum metal inside. We use platinum because platinum is inert and doesn't react. There are H plus ions in that solution. And if you put any metal here and a solution of ions of that metal, and specifically a 1 molar solution, you can figure out, based on the fact that the hydrogen is zero, you can figure out the reduction potential of any of those metals. And so that's what that's based on. The hydrogen cell, not exactly practical thing, but it was used as the standard. And so, without further ado, today we're going to talk about thermodynamically favored reactions. So if it's thermodynamically favored, then the E naught cell is going to be positive. You're going to have a positive delta E. If it's not thermodynamically favored, it's going to be negative. You're going to have a negative E cell. And by thermodynamically favored, we mean that delta G is negative, or non-thermodynamically favored, delta G is positive. So if we look at that reaction, if we want to figure out the E cell, we have to take the reduction potential and either subtract the reduction potential at the anode, or we could change it to the E cell, or the reduction potential, change that reduction potential to the oxidation potential. And so if you look at that, you can do that for any redox. So is this reaction written right here, barium sulfate, lead, when it reacts, is it thermodynamically favored? And so if you look up on the reduction potential table, if you look up barium, find the reduction potential, and you look up the lead ion and lead on the reduction potential table, you'll get these two values. Now, if you look at that, we don't have lead ion reacting, we have lead. So the reaction that's actually occurring is lead is becoming lead ion and 2 electrons. And so instead of reduction, this is oxidation potential, and this is now going to be a positive number. And so I'm just going to take that off. And so if you look at that, we have negative 2.9. The oxidation potential is 0.13. And so if you add those two together, you get a negative E naught cell. And so this reaction is not thermodynamically favored. And so the reaction, or the equation to use with that reaction that would help tell us that, is this Gibbs free energy equation in which you have delta G equals negative Nph, or N, which is the number of moles of electrons transferred in that reaction. So if we go back to this previous slide, if we look at the two half reactions, we didn't actually cancel them out and add the reaction together, but if you were writing the overall reaction, you have 2 electrons in the reactants, 2 electrons in the product that would cancel out, and those electrons are the electrons that we're talking about right here. So in that reaction, 2 moles of electrons are transferred. F is Faraday's constant. Now, Faraday's constant is 96,500, or on your formula sheet is 96,485 coulombs, which is a unit of charge per mole of electrons. And that is a constant. That's what's the charge. That is the charge of 1 mole of electrons. And then when you multiply those two by the E cell, you get delta G. And so if you calculate the E cell, and the unit of the E cell will be volts, and volts are really joules per coulomb. So as delta G becomes more negative, meaning it's more thermodynamically favored, E naught becomes more positive. As delta G becomes more positive, it becomes more non-thermodynamically favored, so delta E becomes more negative. So notice that relationship. Okay, so now let's talk about EMF, the electromotive force, also known as potential, and delta G. Okay, so if we find delta G, we can also find the equilibrium constant. So if you have a reaction, let's find delta G for that reaction. So to find delta G for that reaction, I'm going to want to use negative Nph. Okay. And if you look at that, I can probably figure out N looking at that reaction. I know F. I need the E naught. And so let's come down here. Here's our overall reaction. Look at your table of standard reduction potentials and pick out the reactions from that table. So you have chromium and you have manganese. Now if you look, we have the manganese metal becoming the ion. So this reaction needs to be rewritten to what's actually happening in that reaction up there. So you actually have the metal becoming the ion plus 2 electrons. And so this is the reaction that's occurring. And when you do that, we want the E naught of the oxidation half. And that is positive 1.18 volts, not negative. Okay, and so if we look at that, to find delta G, we want to find the E naught cell. And to do that, let's go ahead and write the E naught equation and then calculate it. So if we put in the reduction and oxidation, and we put that negative 0.74 from that first reaction, and the positive 1.18 volts from the second reaction, and we get a delta, or sorry, not a delta G, an E cell of 0.44 volts when we add them together. And the fact that this is positive means that it's thermodynamically favored. Now the next step is to take that value and put it into the negative Nph equation to find delta G. So if we look at our overall reaction, we found those two reactions. If you balance those two reactions, going back right here, I have 3 electrons here, I have 2 electrons here. To balance that, you would want to multiply this whole reaction by 2 Multiply that by 2, that becomes 6, and this becomes 2. Multiply this by 3, and we get 3, 3, and this 3 times 2 is 6. And so if we do that, we have 6 electrons and 6 electrons that cancel. So it's written a little bit neater for us over here. So these are the number of moles of electrons that are transferred. So if we're using negative inphi, if we have 6 moles of electrons transferred times Faraday's constant, 96,500, times the E naught cell, which is 0.44 volts, you get negative 250,000 joules per mole, or negative 250 kilojoules per mole. Now, the next step would be to find the K. And we want to know, what's that equilibrium constant? And so if we look at that, the relationship that we learned about that is delta G equals negative Ratlink. And so if we look at that, we rearrange this reaction, divide both sides by negative RT. Over here, negative RT cancels negative RT, and you get the natural log of K. So we have that right there. And then you have delta G over negative RT. Okay. And so if we look at that and start plugging in numbers that we know, we have negative 250,000 joules. If we look at R, if you notice for this one, this is not the gas law R, this is the energy R. The units are joules, which will cancel the joules in the delta G. So whenever you're using delta G, you want the energy R. And so that's joules per mole Kelvin times the temperature in Kelvin. And so looking at that, we want to solve this for K. We don't want the natural log of K, we want K. So if we raise this, so we put this e to the natural log of K, and we put this term also e to the delta G over negative RT. This term, e to the natural log of anything, becomes that thing, our K. And so these two guys kind of go away and we get K. And over here we get e to the delta G over negative Ratlink. Or sorry, just the R and the T. So we have the R value, the T value. And so putting those numbers in your calculator, you should get a number that's rather large, like this. 6.6 times 10 to the 43rd. And if you look at that, that's a really big number. 43 zeros are what really go after that decimal. And so if you have a number that big, that would mean that you have virtually all products. So that equilibrium is pretty much all the way to the right. There's hardly any reactants left. Which, going back one, is what you would expect. If you look at the delta G that you calculated, that's a pretty negative number. Negative 250 kilojoules per mole. So that's pretty negative. You would expect K to be very big. Okay, so now let's talk about non-standard conditions. So if the concentrations of the reactants and the products are not 1, if at standard conditions it's supposed to be at 1 atmosphere, it's at non-standard conditions if it's not at 1 atmosphere, if it's not at 25 degrees Celsius. So if you look at that, most cells start out at standard conditions, but the reactants decrease as the reaction goes on. The products increase as the reaction goes on. And as a result, the voltage decreases over time. And so what may start out with an as like say the E naught cell is 2 volts, over time it will slowly go down. And this is what you see with your batteries. So the voltage decreases. Another name for EMF is voltage. The voltage decreases until the E cell equals 0. At this point, you have a dead battery, and this system, oops, that's pretty cool. If I could write again. And that's if that system is at equilibrium. And so if we look at that, concentration, our partial pressures remain constant, nothing's going on, the cell is dead, meaning it's at equilibrium, the concentrations aren't changing anymore. And so if you look at that, you can kind of use that principle. Now, if you look at the Q, and Q is when we're not quite at equilibrium yet. We don't want our battery to be at equilibrium because you'll be dead. You have this reaction. Now, I am crossing off the solids because we're going to look at the things I would expect to affect our equilibrium expression. And so if we look at the Q for a standard cell is going to be the concentration of the products over the concentration of the reactants. And if it's standard, that's going to be 1 over 1, or 1. So if it's not at standard conditions, we're comparing it to standard conditions where Q is 1. And so if you have the situation where you have silver is greater than 1 molar, you have this reactant, this is going to be greater than 1 molar, like say 1 point, or let's just go ahead and say 2 molar. This is 2 molar. What is the new Q? If we look at that, the new Q, our product concentration is still 1. This is 2 molar. And so our new Q is 0.5. So anytime you have Q that is less than 1, anytime you have that, you are going to have a situation where the driving force of the reaction causes it to produce products even faster. So you're going to have, in this case, the electron flow increases, and so the E cell is higher. So if Q is less than 1, you have a higher voltage. Now the opposite is true. If we look at that, if instead for this one, let's say that the silver concentration is less than 1, so you have 0.5 molar over here. And so our Q in that situation is, if we do products over reactants, our product's still at 1, but our new Q is 0.5. So that gives us a Q of 2 now. If our Q is greater than 1, if it's bigger than 1, then our current decreases. It goes down. The electrons don't flow as quickly, and so our voltage decreases. We have less electrons produced in that reaction, or they're not produced as quickly as a rate, and so the voltage decreases. And so let's look at this one. We have non-standard conditions. So again, we have the same thing going on, except now we're going to look at changing our copper ion. Same reaction as the last slide. Now, if we look at this is a solid, so it's not going to affect our equilibrium position. This is a solid, it's not going to affect the equilibrium position. Only our silver and our copper ions are going to affect that. And so let's look at Q for that reaction. So if we have copper is greater than 1, so let's say this is 2 molar, silver is our standard 1 molar, Nothing changed over there. Q is products over reactants. We have 2 molar over 1 molar. And you have a Q of 2. Now, anytime Q is greater than 1, your voltage decreases. It goes down. The opposite is also true. If you have copper, instead of being 2 molar, let's say now this is 0.5 molar. So if we come over here and find the new Q, Q is going to be products 0.5 molar over the reactants, which is our standard 1 molar, to give us 0.5. So now Q is less than 1. If Q is less than 1, then that means the voltage is going to increase. Okay. Now we have changing concentration. Sometimes you might be asked to calculate the new concentration for a reaction that has been going on for a while. So if you have a cell originally under standard conditions, that means originally it was at 1 molar, 25 degrees Celsius and 1 atmosphere pressure. And it's functioning until the zinc ion equals 1.14 molar. Now we want to find what is the silver ion, or it's not silver, gold ion. And so if we look at that, we need to first figure out what is the change in the zinc. So if we look at that, we started out with 1 molar zinc, and now we have 1.14 molar. And so if we look at that, you really only produced 0.14 moles of the zinc ion beyond what was already in there before you started. And so if we take the amount of moles of zinc that was produced, multiply it by that mole-to-mole ratio, for every 3 moles of zinc ion that's produced, you have 2 moles of silver. That's silver. I keep saying silver. This is gold that is consumed in that reaction. Okay. Okay. And so when we multiply those two, we have 0.093 moles, and assuming it's in 1 liter, molar gold ions. So looking at that, now we have gold. If we started out with 1 molar, and now we have 0.093 molar, well, we must, or we used up 0.093 molar. We must now have 0.907 molar gold in our bucket, in our solution. And so now let's talk about concentration cells. Sometimes you can have a voltaic cell. Now that cell can have the same species. And what I mean by same species, you have the same metal at the anode and the cathode. You have the same solution at the anode and the cathode. And so if you look up the reduction potential of 1 and then find the reduction potential, which is the same thing, and you flip 1, like 1's the oxidation number, you subtract the 2 or add the 2 and you get a cell of 0. But you can actually do that with the same substance on both sides if the concentrations are different. In other words, if the concentration at the anode is less than the concentration at the cathode, this will work. And so as the reaction proceeds, the concentration at the anode increases, the concentration at the cathode decreases, and eventually when the concentration at the anode equals, where did we go? Equals the concentration at the cathode, we have our cell is at equilibrium or it's dead and it produces no more voltage. So let's look at an example of a concentration cell. And so right here we have a cell, and if we look at that, we have nickel. Nickel metal is both our anode and our cathode, and it's dipped in a solution of nickel ion. And if you look at that, the electrons still flow from the anode into the light bulb or through the light bulb into the cathode. And if we look down here, we still have our salt bridge. So everything is the same. Now, what is different than before is the concentration. So okay, let's look at electrolytic cells. Electrolytic cells. Electrolytic cells are non-spontaneous, also known as non-thermodynamically favored. And so those redox reactions requires a direct current. So whereas galvanic or voltaic cells actually produce a current, electrolytic cells are the opposite, they require one. And so if you have a cell where you have either a battery hooked up to the two electrodes or some kind of power source hooked up to two electrodes, then you know it's an electrolytic cell. Now, another difference is the electrodes are put in the same bucket. They're put in one container, and they have to be immersed in either molten salt, so you have a solid ionic compound that is heated up to where it's a liquid. And if it's a liquid ionic compound or salt, then you have ions flowing, and you need ions to carry the charge. Or you can take that ionic compound and dissolve it in water to make an electrolytic solution. Electrolytic means it conducts electricity. So the anode takes the electrons from one species, the cathode gives it to the other. So let's look at an example, a picture of electrolysis. So here we have plain old sodium chloride or table salt. So if you have a large container, if you get it really hot, you can melt sodium chloride. And now it has to get really, really hot. And if you do that, these ions are mobile and they will go to the two electrodes. Now, if you look at the two electrodes, these are typically inert, or they're not reactive, and they're things like platinum or graphite. We used graphite the other day for our electrolysis cell. So another thing that's kind of the same, the electrons still flow from the anode to the cathode, but there is a source of energy there, not a light bulb. And so at the cathode, you still have reduction. You have sodium becoming sodium metal, or the sodium ion becoming the sodium metal. You have oxidation going on at the anode. You have the chloride ion becoming chlorine gas here. And so everything else is relatively similar. But, you know, so with this couple of slight differences, there's no salt bridge. There's no need for the salt bridge because it happens in the same beaker. Okay. And so the thing you might have to look at is you have sometimes, if you have an aqueous salt, meaning you have that salt dissolved in water, you have a competing reaction. So you could have the actual ion being reduced or oxidized, or you could have water being reduced or oxidized. So how would you know which one? So if you look at that, we have our two potential reduction reactions. We have in our bucket, we have water because we dissolve this in water. We also have the calcium ion. We also have iodide ion. Oops. So those are the three things we have in the bucket. Now, the two things that could be reduced, we have the calcium ion that could be reduced, or water. So if we look at this, those are the two reactions that could occur for the reduction half. Now, which one actually happens in real life? The one with the most positive or least negative reduction potential is actually reduced. And in this case, this is more negative. This is less negative. So the water gets reduced in this one. On the other side of the reaction, we have to look at what's going to be oxidized. So if we look at that one, we have iodide and water. Now, these two reactions on the reduction potential table, both of these would be flipped. But when you flip them to the species that's actually oxidized, and the water's what's in the bucket, so it's the thing that would be oxidized, you would have to look at that. And again, same thing, that the one with the most positive oxidation potential. Now, since it's the oxidation half, we look at the oxidation potential, meaning you just flip it. So the one with the most positive is oxidized. And if you look at that, that one would be our iodide. Okay, and here is a picture of that going on. At the anode, the oxidation half would be the iodine. At the cathode, um, we have water. Water is gaining 2 electrons and becoming hydrogen gas. So you see the bubbling off of the hydrogen gas, and it's becoming basic. So we have hydroxide ions. Now, if we, let's see, come over here and look at the next one. Let's do the next one. We have electrolysis of a copper to bromide solution. So in that bucket, we have three different species. We have water. It's dissolved in water. Water can react. We have copper 2 ion. We also have the bromide ion. So those are the things that could react. And so if we look up the reduction potential tables of all the possible reactants, we have a couple things going on. So we could have potentially a couple different reactions going on. So we have to pick what's going to actually happen. So we want to know what's the reduction half of the reaction. So to do that, we're going to have to pick out which species will be reduced. And so if you want to know which species will be reduced, we're going to look at copper. If we look at copper, copper is going to go from 2 plus to neutral. So that's one potential reduction reaction. The other is water. Now, you have two reactions with water. You have this one, you have this one. How do I know which one is the reduction half with water? If you look at this, this is the reduction potential table. You have water as a reactant, so I know that this is the other one that could be the reduction half. And so if we look at those two reactions, the most positive or least negative gets to actually be reduced. And so if we, let's go to the next slide. If we look at that, the most positive, least negative is copper. Copper has that more positive value. And so this is our actual reduction half of the reaction. Now, if we look at the other half, if we look at the oxidation half, um, and if we go back a couple, you had, so the oxidation half, when you look them up on the reduction potential tables, these are the ones that are written backwards. So if we look for this bromide ion, and let me change colors for this second half. If we look at this one, this is what's actually reacting. And so this is the reaction that's going to occur, one potential reaction. So I'm going to star that one for oxidation. The other one involves water, and it would go that way. Now, we're going to go up a couple slides where this reaction is flipped, this reaction is flipped, and as well, these reduction potentials will also be flipped so we can find the most positive oxidation potential. And so if we look at that, we have those two reactions to compare. We're going to choose, again, the most positive, or I guess the least negative in this case. And if we look at that, the bromide ion is the least negative, has the least negative value. So we have this value right here, tells us that the bromide ion is the one that's going to be reduced. So if we add those two half reactions, we get the copper 2 plus plus this one. We have our electrons being canceled, and you add up the two half reactions. If we want to find delta G, the first step to finding delta G, we need to do negative N-phi, which is on your equation sheet. To do that, the first thing we want to find is E naught. So if we look at that, we have the E naught cell is the reduction potential plus the oxidation potential. And when we go back, we had the reduction potential for the reaction that occurs. We said that copper is the reaction that occurs. So the reduction potential is 0.34. The oxidation potential for the one that occurs is negative 1.07 volts. And so when we come back over here and we put those numbers in, add them together, we get a negative number, which is what we would expect. We have negative 0.73 volts. This negative number tells us this is not thermodynamically favored. So this is not going to happen unless you add in some kind of energy source or direct current. And that's what we saw, where instead of where the light bulb was for galvanic cells, now we actually have a power source. So find delta G. If we take our delta E that we just calculated, we have Faraday's constant for F. Now this 2 comes from the 2 electrons. Go back to that balancing of the equation. We canceled out 2 electrons in that reaction, meaning that for 1 mole of this to occur, 1 mole of reaction to occur, we have to transfer 2 moles of electrons. So going back, there's our 2 for the number of moles of electrons. When we multiply that, we get positive 140,000 joules per mole, or positive 140 kilojoules per mole. And so this positive delta G, this positive number right here, tells us this is not thermodynamically favored. Okay, so A lot of things are refined. Metals, most metals are found in nature as ores, meaning they are reacted with other elements. And so electrolysis or to our ores or to various things like iron is necessary to get pure metals. So let's calculate. So if we wanted to do electrolysis to get a pure metal, let's talk about how long it would take to plate out uh, 3.56 grams of silver from a solution containing silver ions. So when you silver plate something, you can put a very thin coating of just a few atoms thick of whatever metal you want to plate with. And it's a very cost-effective way um, to make inexpensive jewelry or items look expensive and to have to be protected. And so if we look at that, where would we start? So we want to know how long it would take to do that. And we know we have um, a current of 2.5 amps. And so if we look at that, if we start with 3.56 grams of silver, we start with that and we figure out how many moles of silver um, are in that 3.56 grams. So divide by the molar mass and you get moles of silver. And in that reaction, now if we look at that reaction um, going on, if you have silver ions in the solution and you are introducing it to a power source to plate it to become silver metal, you are transferring 1 mole of electrons for every mole of the silver metal you plate. And so if we look at that, for every 1 mole of silver, you transfer 1 mole of electrons. And if we do that, for every 1 mole of electrons, uh, we know that there is Faraday's constant worth of coulombs, or one for every 1 mole of electrons, there's 96,500 coulombs. Now, I like to kind of get this answer and then go from there. So if you do that, that is, if you stop here, that will give you Q, the amount of charge. And then if you do Q equals IT, you can solve for I, the current, or actually you have a current. You have a current of 2.5 amps. Um, and so if you do this um, for how long? Okay, that's what we're finding, how long. So if you do that, you would solve for T. And so if we rearrange that, we have T equals Q over I. And so the answer you get there, the Q, could go in here. Answer for that part. The amps. An amp is really a coulomb per second. So you might not know where they got that from, but this is 2.5 amps, and amps are coulombs per second. And if you plug in those two numbers there, you could get the time. The answer you get from my equation down here will be in seconds, which is fine unless they asked you for minutes. And I gave you a little bit of time while I was talking. Hopefully you did it with your calculator. If not, do it right now. Pause me and do it right now. 21 minutes. It takes 21 minutes to plate 3.54 grams of silver. Okay, now let's look at electrolysis calculation again. If you had 2 Faradays of electric charge pass through silver nitrate ion solution, Um, what mass of silver is plated out? Okay, so let's start out with you have two Faradays, two Faradays of charge. So 2 Faradays means I have two um, times 96,500 coulombs of charge. Now, I know that for every 96,500 coulombs of charge, that gives me 1 mole of electrons. And then for every 1 mole of electrons, I can do, same reaction again, I can use up 1 mole of silver ions. So if we look at that, if I want to know what mass is plated out, now I know for every 1 mole of silver plated, I have 107.86 grams. That's the molar mass of silver. And so I can calculate the number of grams of silver plated. Okay. Have a good day. And if you have any questions, bring them tomorrow to ask about Electrochem 2. Your problems are attached to this, so go ahead and look at those. And as you will see, you now know how to do all things Electrochem. Bye.